I've been fortunate to spend the last decade at the forefront of robot learning. From attending the very first conference on robot learning back in 2016, to my research at Imperial College and UC Berkeley, to founding the Dyson Robot Learning Lab in London. Now at Neuracore, we're focused on tackling the infrastructure challenge holding back the field. But what excites me most are the conversations with other builders and innovators. That's what this series is all about, speaking with pioneers in robotics, AI, and automation about the technical hurdles, the cultural shift, and the future of working as intelligent machines become part of our world. There's a gap between what we demonstrate in robotics labs and what actually runs in production. That gap is where most exciting research goes to die. So when a company deploys AI systems at scale in real manufacturing environments, it's worth paying attention to how they actually do it. My guest today has been answering that question in production for years. Nima Gard leads AI at Path Robotics, where they've developed autonomous welding systems that handle the kind of variability traditional automation simply can't touch. What makes Nima's work interesting is the scale of real-world data they're working with. Path has trained their foundation model, Obsidian, on tens of millions of actual welds from production environments. So today, we're going to talk about what it actually takes to build AI systems that work outside the research lab. How do you train models when your training data comes from sparks and molten steel? What does computer vision look like when you're dealing with highly reflective surfaces in harsh conditions? And what lessons from autonomous welding might apply to the broader challenges of embodied AI? So Nima, welcome to the show. Thanks so much for being on the podcast.
Of course, yeah, happy to be here.
Yeah, very much looking forward to it. So before we dive kind of more into the technical side of things, I'd love to know a little bit about kind of more of an origin story of how you got into this space, so specifically welding. So what drew you to the problem space, first of all?
Yeah, no, that's a really good question because so I did my bachelor's in civil engineering, and at the time, I was interested in construction and working with buildings and thinking about them, and obviously welding was big part of buildings and structures. At that time, I wasn't really thinking too much about the physics of welding, right? The welding was just being something that we would do, and we would use on steel columns, right? And during my bachelor's, I got really interested in computer science and working with obviously programming and working on it. And towards the end of my my bachelor's study, I got interested in AI. So I started really thinking about it, and then came to the US, did a PhD, and there was a startup here in Columbus, Ohio, that happened to be working on welding and AI. So robotics, AI, and welding. So it felt like it was pulling some experience from the past in civil engineering, and also PhD and masters on computer vision, photogrammetry, and AI. Right, so it was a really nice blend of all of these things that I've done in the past. I still didn't know how difficult welding was. I still didn't know what it meant to properly weld. And by the way, I still don't know how to weld. Welding is super difficult. It's so hard. You have to go to school. You have to get really good at it. Yeah. But now I'm starting to appreciate the physics of welding and really thinking about it, how we incorporate that into our models and basically building AI models that are really good at welding.
Fantastic. And if we think about AI models being used for welding, what makes you think that kind of this is where they can have a real big impact, maybe over some other spaces, maybe?
Yeah. So first of all, manufacturing as a whole is a very interesting space. I feel like it's one of those spaces that we're not using AI as much as we could. There are other places, home automation, autonomous vehicles, and all of that. Great use cases, really impressive results. But manufacturing, in my opinion, is something that is, not a lot of people are coming into it and using AI models. So let's for instance think about welding, since I'm working in welding. Welding is challenging, one, because you have to be precise. Welding is a precise and accurate process. That's one. Two, it is a skilled labor, or you have to be skilled and experienced to be able to weld. You have to go to school for a couple of years. You have to weld for several years to be considered you're an experienced welder. And on top of that, you're going to have variability when you're welding a part, right? And because this welding process is very, very precise and accurate, when you have variability, traditional automation doesn't really work, right? So why do we need AI models? Because we want to handle these variabilities, because we want to be precise, and because we want to make sure that when we are setting up these tasks, they're very easy to set up. And I'm happy to go into more details of this, and where we stand in welding as a whole, and why Path chose to be in a welding specific.
Mhm. And so you've been at Path for 6 years now, right? Around about 6 years, I believe.
Yes.
So, and you spent years now developing AI directly into the production environments, right? So you're not just working in the lab environments; you're actually out there in the real world deploying these like AI models. And so, I'd love to know a bit more about like what the difference is between building models in these lab environments when you kind of have much more kind of control settings versus actually, being able to deploy at scale in like these factory floor environments day to day. Like, how do you go about that, and what's the biggest differences?
Yeah, definitely. I feel like the first thing that we probably need to think about when we're talking about lab models built in labs and for publishing a paper versus models that, or AI solutions as a whole, that are created for solving a real world problem, we probably need to start thinking about metrics. When you're reading a paper, obviously there are benchmarks and there are metrics. And something that I've seen in robot learning that I wish people would start maybe changing it, or make it a little bit more rigorous, is, for instance, success rate, right? What does it mean to succeed at a task, right? If we have to define that, and let's say we are running 100 experiments and only and we are succeeding 90 out of those 100 experiments, right? So the success rate is 90%. But I can run, 200 experiments and then have, chunks of different, sliding windows, and pick the best subset or sub window like gives me the best success rate. Well, when you come in manufacturing, you start reporting a lot more metrics. What is your mean time between failure, right? Not only you're talking about your success rate, but you're also talking about how fast, or how many times you're failing, and what is the time between them. How long does it take to recover from them? What is the severity of that? And what is your uptime? What is the level of autonomy? What is your cycle? And there's so many metrics. So if you have a model that is failing, it matters how it fails. It matters the severity of that failure matters. So for instance, if I'm welding a part and my model makes a mistake, that could lead into a scrap part. That is far worse than that model failing and that leads to a repair, because now I have to throw that part away versus something that I can repair. So in my opinion, the biggest difference is how we're thinking about metrics and reporting them. And obviously, when you start doing that, you start coming up and seeing a lot more interesting questions. If I see my model failing on this specific scenario, what does that mean, right? How can I solve that? Those edge cases start popping up. We were working on this bin picking problem several years ago, and I was really confident in the model, and it was like, yeah, this is working. This is awesome. All the benchmarks are working. And then somebody on the floor came in and put a can of Coke, in the middle of the bin, right? Obviously, the model's been trained for industrial part, and the model stopped working and didn't know what to do. And that gave me the idea of for instance, adding confidence to the models. So I feel like when you're working in the real world, when you're thinking about solving a real world problem, you want to make sure that your solution is actually solving an end-to-end problem, right?
Mhm.
You're not simply thinking about one model for a specific task. You're thinking about the entirety of processes that needs to be done so that you can add value to your customer. And obviously, once you do that, there's a whole rigorous process of testing, rollout, and continuous learning and support.
Mhm, mhm. Yeah, fantastic. And so we've talked about just to then summarize some of what makes welding particularly difficult. Then, so we've got you have to be very precise. You have to come up with some very rigorous and accurate metrics, right? What else would you say is really hard or makes welding a really hard problem for robotics? Is there any other aspects, maybe more on the kind of the sort of the fact that tools perhaps you have to use, or the fact that you're actually using, you're not grasping things per se, but you've got this fixed end effector that can output a lot of heat, and you're doing tasks actually that aren't really covered in academia, right? So a lot of papers that come out, if you're working in home robotics, or you're working in bin picking, a lot of them are directly useful, right, to a lot of companies who work in this space. But I assume a lot of them probably aren't maybe that useful, right? Because you're doing something so different and unique. So how do you kind of cope with that?
Yeah, absolutely. So the biggest perhaps challenge is that there is no data on internet for welding. And if there is, there's very so little data. And if it's for a different process, there are multiple different welding processes, right? So if you find welding data for I don't know, for TIG welding, it might not be applicable to MIG welding. And the way that you have your setup, perhaps the parts that you're working with, right? They might be very different than the data that is available on internet. And one thing that we've done is solving this problem, at least taking steps towards solving this problem as much as we can. And how do we do it? We built a sensor in-house and then we have a fleet of robots, and we are welding every day. So that brings the data that we're looking at. But going back to, so the data is obviously a problem. The other problem that makes it difficult is, again, variability. And so let's go through these different aspects and see how traditional robotics is doing, specifically for welding, and how we're trying to solve it. And then maybe we can go, one by one through them. So if you want to think about tasks in a general way for robots as a whole, we can maybe think about the volume of a task that they're doing, how many times they're doing it, and also the instances or the mixture of tasks that the robots have to do, right? So we have two dimensions, mixture and volume. Tasks then could be categorized in a quadrant of high mix, low volume, and high volume, low mix.
Mm-hmm.
If you're thinking about high volume, low mix, that's where tasks are very repeatable, and we can pay the price of setting the robot, programming it, hand programming it, and making sure everything's good. So that's what tier one automotive industry is. And that's why you see robots have been working in those factories for decades. But then if you change that balance and say, I have high mix and low volume, right? Now you can't use traditional robots anymore. Now you have to do something else. Why? Because the time that it takes to set up your robot might be longer than the time that you actually want to run the task, right? And it doesn't work anymore. Let's take welding as an example. Today, only 20% of welding jobs are done automatically. And they happen to be by the top 1% OEMs, where they can spend millions and millions of dollars making sure that the parts coming to their assembly lines or their welding sections, they're perfect, they're precise, and they spend weeks, months optimizing the flow, the synchronization between robots, and making sure the robot's going exactly where they want to go. So the rest of that 80% is up for grab, right?
Mm-hmm.
There's really no solution for it. So we have manufacturers who can't use automation, and that's happening at the same time that they can't find welders to do these. So it's a perfect storm, right?
Yeah.
And we obviously believe automation is the way to go, and that's our thesis for tackling this problem. So now we're using AI models and robotics and AI obviously to be able to solve this problem. So the models that we have to use now have to be able to do or take care of and tackle uh, different tasks. And for welding, different tasks could be parts that look completely different from each other, and the robot has to figure out on its own how to approach the area that it needs to weld, what parameters to choose, how fast it needs to go. A very interesting, actually, just a side note, a very interesting thing about welding is not only you have to control the robot and the end effector, basically, but also you have to control the welder power supply, because the parameters like voltage, current, wire feed speed, these are the other parameters that are very, very important for welding. You can move really fast, but feed your wire slowly, or you can move slower and feed your wire fast, and you can basically see the combination of this will have an effect on the outcome. So that's one part of it. The other part is variability. So let's say, and then I like to think about the variability again in three different axes. One is, what is your initial condition? Let's say you want to weld these two plates together. Can you always put them in the same exact place? That's what tier one does really well. They make sure they're always in the same place. But a lot of other people can't, so this can move around. And is there variability in the type of geometry? Will I always get these two plates, or would I get plates that look like this or look like that, right? That changes.
Yeah.
And the other variability is, do I see any changes or inconsistencies in how these parts are coming together, right? So a process that is precise, we're talking about less than 1 millimeter, basically tolerance, right? If you're off by more than that, the weld is not going to look good, right? And you have so much variability in all of these dimensions, right? Then you have to have a model that is able to tackle all of these.
And it's interesting you talk about variability, because I think there's a bit of a misconception, right? When people think that, oh, all the variability is happening in like more unstructured environments like the home and shop floors and things like that. But actually, people forget that in factory settings, sure, you can sometimes control certain things, but there is a lot of variability sometimes, as you pointed out, and that's I really want to dive a bit more maybe then into one of the problems we talked about, which is data. This is not just a problem that you have, right? It's a problem that we all have in robot learning. Like, we can't get enough data, but at least in other spaces, we can benefit from the community, because everyone's working on sort of like home robotics or working on, unstructured environments, but not many people working on welding, as we talked about. So I know you guys are very much interested in a foundation model that you've been building. I believe it's called Obsidian. So maybe you could talk to me a little bit about what that is, and your process to go about dealing with building a foundation model when essentially you have to be your own data / internet of data.
Yeah. So our goal is to build to be able to weld anything that we put in front of the robot. Right? So that's what we want to do. And to do that, perhaps we need to have a model that can handle all of these variabilities that I just talked about. On top of that, you have so many other factors that go into it. So it seems like the foundational model is the right recipe for solving this problem, because you want generality as much as possible, and you want to be able to tackle new cases that you might not necessarily have a lot of data for, but you want to benefit from the data that you collected for other cases. So it seems like foundational model for welding would be a really nice thing for that. But the challenge is, well, how do we get data for it if we can't find data on the internet? So Path was started 2000, 2018, and obviously before that, the founders were working on the idea as well. But we started at a time where robot learning and foundational models were not as, it wasn't a hot topic. It wasn't, as hyped up as it is today. And that was, I feel like, a really good time to think about how to build your data engine, how to build your data flywheel. So we spent a lot of time on building a sensor in-house. And I'll talk about why we did that, why the thought process behind that was. But at the time, we decided to work with models that were specialized, models that perhaps were classical with heuristics, but we prioritize getting out of our four walls and going out on the floor. The other thing that is very important in welding and manufacturing is, yes, we don't have the data, but also the parts that we need to weld, they're very expensive. So, maybe in manipulation, obviously it's a very difficult problem, but you can go buy an Apple. You can 3D print things. You can do those things that are sort of cheap. But if you're welding a truck chassis, if you're welding a 60-foot long utility pole, or I don't know, a pressurized tank, this is not going to be $10, $20. This is going to be an order of, hundreds of thousands of dollars, or I don't know, tens of thousands of dollars. So you can't really, go buy a whole bunch of those and, start experimenting. So the idea was, the thought process was, let's get our robots out as fast as possible, and let's just start collecting data.
Yeah.
But that obviously came at the cost of, we don't have a lot of data and we can't have general models. That's okay. Let's, try to solve that with specialized models. Maybe one model for one customer for a specific part, and then another model for somebody else. But then over time, 6-7 years later, you have all of that data available to you. Now it is the time, perfect time that we have a lot more progress in robot learning and foundational model, and recipes are becoming more and more apparent. But the key thing is the data, and I feel like we were I guess lucky / had the foresight to think about that ahead of time. So that's the story, and that's very similar to think about autonomous vehicles. They they build a car first, and then they have people drive it. They don't have autonomy first, but then as you collect your data, you will start adding autonomy.
But if I'm not mistaken, the difference here is that they would have, with self-driving cars, they have maybe people driving them first. But just to clarify for anyone listening as well, but yours are not kind of remote controlled, right? You're not doing teleop. You actually do design autonomous systems, but they're just specialized for each customer, right?
That is correct. Yes, absolutely. So the customers don't know, what's going on behind the scene.
Right.
We are, using, specialized models, but then, going to the next customer, we want to make it easier because we want to, improve our bottom lines. If you just keep doing that and output more and more cells, and then, keep hiring more and more engineers and, develop more and more models, this is, never gonna, catch up. So you want to make sure that you're optimizing your solution from our side, not from the customer side. The customer side is still the same experience, obviously, improving in performance as well.
Yeah, fantastic. And we've talked a bit about data that you're collecting, and I know you've talked about this in-house sensor. So maybe we can go into a little bit more details. Exactly what is the data that you're collecting? Is it just this in-house sensor and that's it, or is it RGB camera data you're collecting as well? I'd be just curious to know a bit more about what that looks like.
Yeah. So the sensor that we're building in-house is a collection of several different scanners, or several different sensors creating a scanner. However we want to think about it. So we have 3D data, we have 2D data, we have 3D data as we're welding, we have 3D data before we're welding, we have 2D data before welding, we have 2D data after, during welding. So there are different phases and there are different modalities. And so there's a lot of visual data, and they're all kind of tied back together. So there's a really nice way to go if you want stereo versus you want, mono versus you want, I don't know, depth or 3D, you get nice access to that. But the challenge is, how do we make a sensor that is, small and compact? We want a compact form factor because we're trying to get into very small and tight areas, right? I don't know, maybe if you're, again, I'm going to give that truck chassis example. You're trying to get into a, tight spot. You can't have a massive scanner doing that. So you want it to be small. And the other requirement is you want to be able to capture data under different circumstances. When you're welding, it is super bright, it is super hot, and you want to see what's going on, and you want to also see you want to see the puddle, right? And at the same time, when you're not welding and everything is normal, you want to see what's going on, like an RGB data. So when we started the company, obviously there were sensors that were specialized for these different modalities, these different stages, and what we needed was one single compact scanner that could do all of these. And now that I think about it, when we started, they were our sensors were massive, but now they're getting a lot smaller. There's so much thought that has gone into creating this sensor. We have an amazing team working on this scanner. They do a lot of testing on vibration, thermal. There's even, just to give you an example, there's this little shield that is in front of the cameras, because as you're welding, spatter goes everywhere and it might hit the lens.
Right. Yeah.
Obviously, you have to protect it. But what is the material of that? And how do we choose the material such that the spatter can roll over that protective film, and you can easily swap it in and out. So it's a consumable. It has to be cheap. It has to be durable. So a lot of that has gone into that that piece. So well, with that scanner in hand, and using it across our fleet of robots, then we've been able to collect the data that we're using today.
Yeah. I mean, gosh, it's quite a unforgiving environment then, right? That your sense has to put up with, and I guess that probably influenced why you went for real data, right? Because you're going to be dealing with reflective metals and smoke and spray, and as you just talked about, heat and sparks. So I mean, I can see why, for example, say simulation might have been a non-starter. But I'm just curious about your thought process around simulation, especially when it came to gathering data for your foundation model, Obsidian. Did you consider simulation? Did you think that it was maybe worth investigating, especially as simulators kind of progress, right? And the vision gets better and better. I'm just curious on your thought process of that and where simulation fits into this. And do you see simulation maybe becoming a bigger part for Path as you go on over the years?
Yeah, absolutely. So this welding model, is one of the models that we're building Path. But vision system that you talked about, it also has its own neural network, right? Because we are trying to drive modalities from the modalities that we created, right? If we have, let's say, stereo cameras or images, we somehow want to create 3D data, right, from that. And so we can and we are using a neural network to do that as well. And we use simulated data for our different part of our vision system. So we're not a shop that say no, only real data or only simulate data. It's fit for purpose. If it works, great. If we can easily create it, wonderful. We will use it. Welding, yes, we considered simulation from the get-go, because that would be nice if you could generate millions and millions of inches of weld. I don't know, in a week or two, right? Just spin up a bunch of nodes and start simulating data. So we looked at several different solutions at a time. We worked with somebody who actually did a PhD in simulating weld. And what we found out was, again, these simulations were not at the level that we need them to be, especially for welding. As I said, this is a very precise and accurate process. So instead, we said it would be nice if we could learn the physics of welding. It would be nice if we could have a neural simulator. So we still want to be able to simulate different scenarios, but we want to ground it in reality and incorporate physics as much as possible. And that's the thought process behind getting data as much as we can and creating this neural simulator. Now we can call it neural simulator for dynamics or world model. It's basically you have the state, you have the action, you want to know what the next.
What happens next? Yeah. Mm-hmm. Fantastic. And I want to talk a little bit about human data collection as well, but just to finish on that point with the simulators and the world models, have you played around much with some of the world models that are coming out, and how good are they on these environments that you deal with? I mean, I can tell you my experience with them from a home robotics perspective. I mean, they're pretty awful. They're pretty bad when it comes to any sort of robot, because the data distribution just doesn't see much of that. But I'm very curious if you've played around with it. What sort of generations do you get when you kind of plug it in with some factory data?
Yes, yeah. So we are more interested again in welding itself, right? Mm-hmm. So these world models are not going to be even remotely useful for that. I have played with them just to see what it looks like for other tasks in manufacturing, and as you mentioned, it's very, very dependent on the type of data and the distribution of data they've been trained on. I am, though, very interested in world models and how they could help robotics and robot learning in general. But I feel like we're at the beginning of an exciting journey, and there's a lot more to be done.
Yeah, absolutely. Great. And so shifting back now to real rather than sim, there's a lot of interest, I guess, in acknowledging that collecting data on real robots is difficult and expensive. And so there's a lot of interest now in kind of like semi-passive data collection via humans, right? So egocentric data, for example, like getting people to wear cameras and gloves and haptic gloves, et cetera. And of course, then we've got things like UMI grippers, right? Which is where you shove a camera on a thing and you 3D print a gripper. Is that possible? Is there like a UMI style gripper for welding, right? Where you could actually get this on real welders that are, I believe you said it was 80% is currently not automated, right? So could we take that 80% and put some cameras on them and gather data?
Yep. Yeah, absolutely. One of the ways that we collected data for our vision system to make sure that we can see through welding and be able to capture different environments was like I said, we couldn't we could, but it would be very expensive to start buying these massive parts and bring it on site and do that. So a while ago, we didn't call it UMI, but a while ago we had this embodied scanner that we created, right? In the robot, you can just make it a handheld robot, right? And we would go on different factory floors, and there were parts laying on the floor. You have your embodiment, so you're just moving it around, and you're capturing the data that you need. So we've been doing that, but obviously this UMI, this universal manipulation interface, is kind of a newer term, mostly for manipulation.
Right.
But yes, I feel like we've been doing it, but obviously we haven't talked about it or marketed that way. So is it possible? I think so. It's definitely an exciting route. Having cameras directly or egocentric, I think that's an interesting idea as well. But very similar to imitation learning, right? If perhaps your embodiment is very different than the expert embodiment is different than the embodiment that you want to eventually roll out. Obviously, there are some considerations. There's not a one-to-one mapping. You have to think about, retargeting and all of that, and that probably will create, some other, work that you have to figure out how to do that directly from a human, rather than the end effector itself being manipulated by a human.
Okay, fantastic. So I'd love to talk a little bit now about what's it like to actually deploy a system like this. So you've got your model that you've trained, and now you're actually deploying it out into to customers. And as you and I both know, getting something to work, in one place and for one system is hard enough, but getting it to actually scale across all your different customers who probably have like slightly different requirements is a whole other challenge, right? Entirely. So I'm quite interested to know about when this happens and when you kind of like ship out your solution, what tends to start to break first, and kind of how do you react to that, and how do you iterate? How do you learn from that in order to improve the model in the future?
Yeah, absolutely. That actually brings back some memories of the first deployments that we had, going to the first customer and just looking back at that. AI models are obviously important and a big part of a solution that adds value to the customers, but they're not the only part. There's so many other things that has to happen for this to work. And at the time when we started, we were trying to push as fast as we could, to learn as fast as we can. And, perhaps our release strategy, our, branching, our, configuration management, internet connectivity, and so many other things where we're just, let's just go out to the first customer and see what happens. But, as you can imagine, if the infrastructure and the scaling around your model is not as robust and as scalable as it needs to be, it's going to be a problem. So when you go to more sites, you start to think more and more about all of that. So today we have an incredible team on the platform and the software engineering who's thinking about these things. We're always want to make sure that these updates go smoothly as possible, without any hassle. We want to make sure that if I'm changing on something on this customer, I know what I have changed, and we want to be able to track everything. And when we are supporting the customers, we want to make sure we can do it remotely. So we have a team, our mission control, 24/7, and they're there to make sure that everything is going great, and if there's any problem, they're there to help. So when we're thinking about a fleet of robots and making sure that we have customers who are happy, not only we have to think about the performance of a model and all of the metrics that I've talked about, but also everything else that goes into this, which is software, hardware, operations, mission control, and all of that.
Yeah, a lot to think about.
Yeah.
So I'm interested, obviously, you know my interests are in kind of like broader robotics and like unstructured environments outside, in like say home environments, around humans, etc. So I'm very interested to hear your thoughts on, like, broadly speaking, essentially lessons that you've learned at Path. Let's just say right now you decide, okay, we've conquered welding, and you've solved your goal of being able to weld any object. I think that was the mission statement, right?
Yeah.
And you've done that. I'm very curious now, what would be next? Like, let's say, okay, what are the lessons that you could take to forward to a new problem domain? What would that problem domain be? And kind of B, why that problem domain over others that you think shares some similarities with welding, and you could transfer some of the skills that you learned?
Yeah, that's a really good question, and the reason for that is because there are so many different processes in manufacturing that are just waiting to be automated. Throughout the entire sector industry, we are experiencing shortage of labor, and specifically skilled labor. And welding is being one of them. We decided to go welding at first because we're thinking that we are approaching a critical problem, and the shortage of skilled labor is going to be impacting a lot of different manufacturers in the country as a whole. But then let's say we solve that. Now, what's next? Well, when you think about welding and you go a few processes upstream or a few processes downstream, you still see there are highly skilled tasks that they need to be automated, because we still have shortage of skilled labor there. So if you go one step up, that's where the parts need to come together.
Mm-hmm.
That's where we need to assemble things. If we go one step up from assembling parts, that's where perhaps we need to, cut those big sheet of metal, and we have to form them, and we have to prep them in a way that they would be, they would be in the shape that we wanted to put them together and weld. And if we go down from welding, now we need to perhaps polish the surface, or we need to grind some areas of that part. Then we need to paint it. Then we need to palletize it. Then we need to pack it, and so on and so forth. So there's so many steps prior and post welding that are super exciting. There's massive need for them, and they are still fall under the category of high mix, low volume, and they fall under the category of skilled labor. Those are the type of labor that you have to perhaps go to school or trade school, or train for a long time, as opposed to folding cloth, or folding other things that you could learn quickly. So how does welding and the lessons learned from welding can help us? In my opinion, the first thing is really thinking about a solution. Again, building a model is challenging, but it's not the only thing.
Mm-hmm.
If we are trying to solve a real problem, there's so much other thing that goes into it that we have to think about. And having an infrastructure already for welding would definitely help. We don't need to reinvent that whole infrastructure again. We don't have to think about what it would look like to collect data at scale. We've already done it. We have a lot of experience with creating these tools and scanners for welding. Right, we could use that experience for other tasks as well. We've gone through iterations of how to improve models, how to start small, and add value as we go. So there's a lot of lessons learned from operations, from business side, from engineering, and all together it will make doing another task and automating it a lot easier.
Mm-hmm. Fantastic, yeah. And I have one kind of question to finish off here. So I'm curious, as we've already discussed, there's not a lot of direct work that you can pull from the robot learning community, because the application area is quite different, but the problems you face are very specific, right? But I'm curious that if you could kind of have a magic lamp, and you rub it, and then you get to have a single wish that the research community would work on, problem would work on. What would that be? What would be the one thing that you wish someone would just solve that would make your life much easier and be able to make Obsidian 10 times better?
Yeah.
And I know we've talked a lot about different problems. We talk about metrics, we talk about the data, the variability. What is the number one thing that keeps you up at night, basically, that you want someone to solve?
Yeah. So I would again go back to I'm not going to talk about the methods specifically. I really care about reproducibility of some of these methods. If there was a way that we could know some idea, some method, it is reproducible, it is actually we know that it's going to work, or somehow it would be very, very easy to test out these ideas, as opposed to spending so much time setting up environments, figuring out how to get the data in a shape for that, and things like this. And I'm actually really grateful that you are helping in that area a lot with Neuracore, because you are setting up that infrastructure. You're making it a lot easier for different people to be on that unified layer and infrastructure. So I would say, I don't know, Stephen, just make it grow faster.
Yeah, we need to move faster. We do our best. Well, on that note, thank you so much, Nima. It's been really, really great having you on the podcast. So thanks a lot.
Thank you so much.